Alrighty, so it is 6:30, so let's go ahead and get started. Anybody comes in late, they'll catch the VOD on YouTube. So we're going to be talking about the Unity's data-oriented tech stack, which they have been talking about for a number of years now, and they kind of went dark for most of the pandemic, actually, and they've just recently, I guess, back in March-ish, released their .5, .50, I guess they're calling it, .50 and .51 versions of the ECS, the Entity Component System. The DOTS stack itself is more than just ECS. It is also the job system, the burst compiler, the mathematics library, and there's also a new Unity collections as well. Everything besides the entity system itself has been live for about a year now. It's been in 1.0. They say that the entity stack, the entity system, will, they are aiming for the 2022 LTS version, which is usually like Q1, Q2 of next year. So in roughly a year or so, this will be fully ready for production. So this slideshow here I want to go through real quick is actually one that I did back in 2019, about the time they were first doing a real big push introducing the tech stack. So we'll just kind of see where it started and where they are right now. Tell you up front, not a whole entire lot has changed, but there is some API changes, some usability stuff that we'll go over, and some assets that have come out that utilizes the data-oriented tech stack. So just for super quick intro here, like what even is ECS? And this is a data-oriented design, which is kind of different from the object-oriented design that you might be used to in like traditional programming. So the entity component system has, as the name suggests, it has entities, it has components, and it has systems. So the entity is literally just an index of an array. And the way that the ECS works is that it will lump all of your data in memory contiguously. So that way the processor can do massive amounts of work on all of, say, your positions. So all your vector 3s, it can just go through like 10,000 of these things all at once, all through memory, and you don't have to worry about, they call them cache misses, which is when your CPU that has your like L1 and L2 cache, when it has to go out back into memory, into your RAM to get a piece of data, that's a cache miss. So in order to avoid that, what it does is it will line up all of your components in memory in a single array. So like this little picture here, dude's holding a speed array. So if you need to go through all of your speeds, you'll get that first speed and also the next chunk, which is I think is like 16 kilobytes of those speed floats for free. And that is how DOTS gets performance by default, is what they like to say. Now, so you have all of this data in chunks in your memory. What do you actually do with it? You have systems. So your systems is what is the actual functions that your data gets worked on. So we'll have a movement system, a render system, a physics system, a network system, input system, all that good stuff. And so, yeah, that's basically how it also makes multi-threading easier. This is what the job system is for. So once everything is contiguous in memory, then it's easy enough to break those chunks into smaller chunks, throw them out to different threads, and then have the system work on those different threads. Man, this is old. So this is was accurate as of 2019. We'll go over some of this. A lot of this has actually changed. So they used to call this a hybrid workflow where you started out with game objects and then stuff got converted into entities. It's no longer hybrid. This is just the way it's going to be done, which is good all around because you don't have to change the way that you normally work. You can still have game objects in your scene that you work on, so your level designers can still design levels and all that good stuff. There are other systems here that are not live and not being actively worked on, like the animation system is the biggest thing that's missing right now. But they are kind of all hands on deck trying to get the ECS up to 1.0. So the animation system, the audio system, those are kind of on the back burner until after the 1.0 release. Networking is, there is a netcode for entities that is working. The physics is active as well. So that is there's Unity Physics and Unity Havok, which I think is here eventually. This absolutely did not happen. So that was the original plan, was to have entities 1.0 back for 2020. The netcode is actually coming along. I think we have a demo of that here that we'll show a little bit later. So yeah, the physics is in the package manager now. So there's Unity Physics, and then there's Havok Physics, which I believe at this point, yeah, Havok was bought by Microsoft at this point, and so they are working on a separate physics engine that you can easily like flip between. That I believe they both just have the same APIs, but Havok is more stable for higher entity counts than Unity Physics, which I think is just faster. Don't quote me on that. We'll take a look at some of that. So yeah, a lot of this stuff was in the works. I think it is still experimental, but don't expect work to be done on these anytime soon. Same with the animations. The visual scripting, they bought Bolt since this slide was created. So I think they're just folding the Bolt visual scripting system into all of this. Then we got some links. Most all of these links are actually still good. They are updating the entity component system samples. They've got those fully updated. And also there is this data-oriented design book, which is free online, which I believe should be required reading for everybody actually. So we don't need to go through a lot of these, but the job system is Unity's multi-threading system. We'll go through how to write jobs and how to schedule them and all that good stuff. The burst compiler is a subset of C# that is highly optimized for speed. Most of this is done by default, so we don't actually have to explicitly tag jobs for the burst compiler, I believe. So this is just kind of the default how the burst compiler will just work. Multiplayer, we're not going through most of this. I will say that they have the game Unity Game Services has matchmaking and server hosting. They bought Multiplay, which is a server hosting service that I believe Apex Legends is using it. But that doesn't really have much to do with the ECS at all at this point. The transport package, I believe, does use the job system, but that's for another talk. Same here, we don't need to go through that. And physics, so. All right, so now we can just hop in some demos. Okay, so this is the URPS samples from the entity sample package, which is entity sample project, which is here. This has been updated in the last few months. It's got your ECS samples, your URP, HDRP for the hybrid renderer. We'll support both. And physics, we'll go through a few of the physics examples and see how well they run on this laptop. This is a i7 laptop with a 2060 GPU in it. So here in, let's see, what's a good one to look at? We can look at the creation API. This will work to start out. So with the .50 version of Entity Component System, they have updated the Unity packet, the Unity version that this will run on. So it is now current to 2021. If you use the 2022 version of Unity, the sample packages will not work. And I think the ECS system as a whole, I don't think will actually work. So this is basically what the what the package comes with. And I'm not sure why entities is not showing up here. We do have platforms, we do have the hybrid renderer, custom in unit. This might not work. Let's see. Hey, you did. Okay, so what you are seeing here is 10,000 entities got created, 500 on the main thread, and this is the actual formation for the spiral twisty thing here. If we open up the API here, okay, so this is kind of the bare minimum for using entities here. So this is going to be on a mono behavior for the creation API. We have our some of our variables here that we saw in the inspector. We also have this job, which is a strut. And this is a parallel job. So this job specifically is going to be tossed out to our various CPU threads. And all this is going to do is spawn our, no, actually all this does is change the color and set a transform. Not going to go too far into like entity command buffers and all of that good stuff. But needless to say, the execute is the actual function that is going to be happening on our threads. So all this is doing is it is grabbing our entity command buffer here, which is a parallel writer. We're calling instantiate on it, and then we give it our entity, which is this index here. That's our entity, and the prototype, which is just an entity that we will give it when we actually schedule this job. So the prototype is basically just like a prefab, but it's just an entity that has components already on it. The entity command buffer is how we'll actually make changes to our entities. You could, in theory, just set the components directly in the job, but that creates various sync points, which have to be run on the main thread. So if you don't use any command buffer and you just try to use, there's an entity singleton that you can use to set components and change things. If you do that, then that will force jobs to have to wait and then complete on the main thread, and then it'll do its thing. The command buffer, like it suggests, it will buffer all of these commands and then run them at a later time in the frame. We'll look at some of the new editor windows that help you visualize what is all going on here. Okay, so what this is doing here, this is setting this component. This is the index of the loop. This is actually our entity that we just instantiated. We're giving it a local to world. We'll look at, actually we probably just see that here, not yet. We'll look at that in a second, but local to world is basically the transform. So we are giving it a value of compute transform of this index. This compute transform basically, it creates that spiral formation based on time. Well, I guess it's just where it is in the order that it's being spawned. And same with the color. This compute color is just setting the material color. And there is a renderer system, which is the hybrid renderer, that will read local to world to figure out where this entity is going to be spawning, and then there's a material color that will give you said color. Then in start, real quick, the entities all live in a world. You can have multiple worlds with different sets of entities. We can see that in the multiplayer and physics. There's a physics world where all of your physics calculations take place. The default world is the object injection world. This is where things that are created in the editor, when they get converted into entities, they get placed in this default object injection world. Each world has an entity manager that will manage all of its entities. So for the most part, what you'll do is you will grab the world, you'll grab that world's entity manager, and then you can also create various command buffers. Usually you only create one. This one is just for demonstration purposes. So this first ECB job here is the first command buffer. It's going to be what's going to be thrown out into the job system. And then we have this main thread here, which will be running on said main thread. We have the render mesh description, which is just everything that we need for our render mesh, which is the mesh renderer and ECS terms. This is our prototype, which is like I said, it's kind of like a prefab. So you'll just take your entity manager and you just call create entity, and this will kind of allocate a index in all of these arrays for this entity. So we have a prototype, the entity manager, and then the description here. So we are adding this render mesh utility is going to add a render mesh to this entity. And then we are also going to add a material color here for this entity as well. And then this prototype is what we're going to pass in. Here we actually instantiate a new job. We give it the prototype, the command buffer, the number of entities, our object scale, the radius of our spiral, and the number of twists in our spiral. And then for this job, we're going to subtract our main thread entity count, because this here is going to be what's called on the main thread, which is not recommended to do. So after we have our job entities, we have a spawn handler, and then we just schedule this job. So this line here is how our job gets scheduled. This is the number of job entities, so each job is going to be one entity. And then the inner loop batch count, I believe, is just how many jobs per thread. I believe that's what that is. So for this one, this is not a job. All of this is happening on the main thread. So we are basically just doing the same thing, but we are just setting the component here, and then we're adding a material color component to these, whatever, 500 entities that we've got here. Again, this is just for test purposes, just to show you that this does actually work on the main thread. It doesn't need jobs. And then what we'll do here is our spawn handle that we grabbed for our job schedule. We can force all of these jobs to complete, which they need to, because this is going to be the first thing they all need to complete first before we call our job playback. So this is the entity command buffer that we just filled up through our job schedule. you play those back at, I believe it's the end of the frame. So once you play it back, this will actually just roll through all of those commands, create all of these entities here, and then we dispose of it. Then we go through and we have our command buffer from the main thread. We play that back. And then we can destroy our prototype game object. Okay, so I know that was a lot, but we'll hop back into Unity and show what this all actually looks like. So as you can see here in our regular game object hierarchy, you're not seeing any of these cubes. Even though they do show up in the scene, they are actual cubes. But I can't click on them. I have no idea what they are or anything like that. That is because these are all entities. So the new things that they released with their .50 and .51 are these dots windows. So we have a window for our hierarchy. We have windows for components, systems, and archetypes. The archetypes are the collection of components for our systems to actually work on. Back in here, our prototype is an archetype. So everything that has this local to world and material will be an archetype. So all of your archetypes are grouped up in an array, and so all 10,000 of them will be back to back in an array that we can cycle through extremely quickly. And those will be chunked together in 16 kilobyte chunks. So every time you get one, you'll get the other 16 kilobytes right after it for free. So let's look here. We can look at our dots hierarchy. So this is going to be something that they're going to be working on and improving as it goes towards 1.0. They say that their goal is to have a single hierarchy that will have both your entities and your game objects in it. But for now, it is, we'll just put that here. For now, all of our entities are just in this stack here. They want to add an actual hierarchy, so it's not just this insanity here. Each entity has, you can click on them. They will show up in the inspector over here. We'll look at a couple here, but you'll see here, you hopefully will be able to see this on the video. But next to entity, in parentheses, you have this index, and you also have a version number. So whenever an entity gets destroyed, this number here, 1287, will get freed up, and then the next entity in this archetype that gets created will get created right here as 1287, but it has a version number will be like 2. And that's how you can kind of keep entities kind of straight while you are doing, all of your parallel work to it. You can also name these entities as well, just in case you didn't actually memorize what entity 64 actually was. But 99% of the time, you're not even going to care what entity number 10 is, because we have this archetype. So these here are components over here in the inspector. So we have a number of built-in ones. We also have this local to world. This is important because this is a 4x4 matrix that will give you your position, your forward vector, your up vector, and your right vector. I don't think it'll let us. I can't tell whether that actually works or not. Eventually, we will be able to click on these and actually move them around. I guess you would have to see them in game view. In the scene view, this is actually what this will do is you have this conversion setting here. So the conversion settings is actually what will happen when you hit play mode and your game objects convert into entities. You can just straight up have them destroy themselves. Like if we'll look at the other ones in a second where that does actually happen. But you can just have them destroy themselves from your hierarchy, so it just shows up in the game view. You can also have it here, live conversion authoring state in the scene view. So the scene view will stay as it was when right before you hit play mode. And then the game view will be what's actually happening in game. You can set it to be the runtime in the scene view if you so choose to do that as well. Okay. Missing partial keywords. This is something you will see if you are upgrading from the older ECS system. Like the one before this one was 0.17, I believe. If you're upgrading from there to 0.50, you might get this missing partial keywords to systems. Systems need to be, I don't think we actually have any systems in this particular one. Systems will be partial classes because there is a lot of generated code that's going on in the background, which is part of how the burst compiler works. Okay, so you have these built-in components here. We also have the one that we added, which is the render mesh. We added that. And yeah, I think that was all we actually added. And then with this local to world tags. So tags are just components that don't have any data in them. So you can use this to kind of signal events or anything that you want to filter out. These 10,000 entities don't all have to have the same components and tags and whatnot. So if you want to do something to, say, half of these, we could have placed a tag on like every other entity. We can have a tag to delete itself or something like that. And then in our system, we can just look for this tag and then do our work on it. We'll show some here shortly. Okay, so what probes? Trigger particles. Okay, this is a good one. It's a really simple one. Okay, so this will show you how subscenes works and also how you can trigger non-entity things through entities. So this is going to be triggering a particle system to play when this ball hits the ground. Technically, it's not doing a collision check or anything. It's just when the y position of the transform hits 0, it will trigger said particle system. Particle system is not real important. So here we have a subscene, which is what our ball is, and also what our floor is under. So right now, this scene will just automatically load when we hit play. And it will load and also convert these objects into entities. If you want to see them in your editor to do whatever with them, you load it. So you just open it up, you'll hit the check mark, bam, they add in your scene here. You'll also notice that in our dots hierarchy, we have an editor world, which also has our subscene in it. So we have our sphere, we have our particle system, which just will play some spheres. We have our ground. So what is going to happen here is that all these components, you'll see they have convert to entity here. This is kind of the new system that we have. And we will, when this hits play, all of these will get transferred, or I guess converted, into entity components for this entity. So our mesh renderer will get converted into that render mesh component. Sphere collider will get converted into a physics shape. These are colliders. They're called physics shapes. There's also a rigid body, which will get converted into physics body. And then we have this jumping sphere tag authoring script. And this will just add a jumping sphere tag onto the sphere. We'll look that up here. So all of your components have an iComponentData interface on it. So it's just a struct with iComponentData. For tags, best practice is to just put tag at the end, just so you know that there's no data for this jumping tag. So we could technically, if you wanted to add like a float to this to say how high the ball will actually jump, you could do this. We're not, because we only care that this is going to be jumping. Now, to throw this onto a game object, you need to put the attribute here, generate authoring component. And that's all you need to do. So once you have a generate authoring component, you can then throw that onto your sphere. And then once we hit play, you will see that sphere will have a jumping tag on it. We also have this jumping sphere tag, the sphere PS tag, which is the particle system tag, which we put on the particle system. Down here. So here we get to an actual system here. So the meat of it is we have system base, which is what all of our systems have to inherit from. And it's got to be a partial class. So we have various callbacks here. We also have it here, and then we have all. Will it come up? Maybe. Protected. Maybe. Override. Void. Yeah. So we have on create, on destroy, on start running, on stop running. So these basically map to what you expect from Mondo behaviors on start, on awake, on destroy, on disable, on enable. You will basically do like initializations and whatnot in your start running or in on create. All of these will run on the main thread. So your on callbacks, all of this will run on the main thread until you get to your actual job. So since this is on the main thread, your jobs, since they're on other threads, they can't grab time.delta time, time.elapsed time. So we have to grab it on the main thread here. Also, if you're doing inputs, you would grab your various key presses and whatnot outside of your actual job. We're also giving it this Y component, which is just a cosine wave jumping up and down 3 feet, or 3 meters or whatever. So this is kind of the most straightforward way of making a job is using this entities.forEach. So this for each here is the query that we roll through for all of our entities. It will look for everything that has a translation component on it with this tag. So this tag is not going to be taking up any memory, mostly because it's empty, but also this with all here is specifically just for tags. This translation here, it is a reference to the translation. So that means we have read and write access to it. There is an in keyword that will just give us input, which is read-only access, which the burst compiler will do some various optimizations for read-only data. We don't care if anything else. We don't have write access, so we can do different optimizations in the background for that. And then there is, I don't think we do out here. But basically, you have read-only and in, and then reference is read-write. So since we are changing this value for translation, this has to be the ref type. And then all we do here is we have on the components have a value to it. I think we can just definition. Right. So it's just a struct, component data. It has a float 3 value. Float 3, if you're not familiar with it, it's actually just 3 floats, but it is equivalent to your vector 3s in the monobehavior world. But vector 3s are actually really huge classes that have all kinds of baggage and overhead to it. This float 3 value is literally just 3 floats. And it's also a value type instead of the vector 3 reference type. That helps with your cache misses and all that good stuff. Okay, close that. So yeah, so we just set that to a new float 3, just bouncing up and down, and then we schedule parallel. Now here, we actually have a separate job that is, it has to be run without burst because it is using the particle system, which is not in the entities world. So we can't burst compile it, but we can still have our sphere particle system tag, and then we will reference it, so it has to be on the main thread here, and then we just, if we are less than 0.05, then we just call our particle system.play. And then because it's on the main thread, we just call run, and then that will run it on the main thread. Schedule parallel and schedule both run these on our various threads. There we go. Okay. So we can actually just unload these. It really doesn't matter either way. The way the subscenes were meant to be used, if you remember a couple years back, there was a Mega City demo that was like this really cool, like Blade Runner flying car simulator thing. That had just a ginormous amount of buildings and cars flying around, traffic and whatnot. And like your various sectors were subscenes here that get loaded and unloaded to help actually in the editor. So your editor doesn't get bogged down by, 100 million entities that you don't really care about because you're not close to them. You can also give it a hierarchy color here. So if you have a crap ton of subscenes here, it'll just give you a little sign of like where they are actually in your hierarchy. Doesn't actually do anything beyond that I'm aware of. But yeah, it also has this auto load scene, so it'll automatically load it in your game. Let's actually open up a couple of other windows here. So we have our systems. I'll dock this down by the console, but for now, we actually will need the space here. So these are all of our systems. You have your various worlds. Right now, we're just an editor world. For multiplayer stuff, you will have a server world, a client world, physics world, I think, gets added when you start doing physics stuff. But these are all of our systems. Most of these, all of these, will be built-in systems. You have system groups, which basically just divides up when these systems are running. As you can see, they are actually running right now in editor mode. We have our various simulation groups, fixed step simulation group, variable rate transform system groups, which will, like I said, works on our actual transform. We do have 3 objects, I believe, currently with the local to world transform, which is the sphere, the ground, the particle system. We can turn these off and on as well. And here's our weight update stuff. Our sphere particle system should be in I'm actually not sure where that's actually going to end up being. We'd be able to find it in our inspector when we hit play. Also, you can just search for it. Yay. So we can look here. This is our number 10 here is our particle system. We can look at our tags. We have our jumping sphere PS tag. We also look at the relationship. So these are all of the systems that are querying this particular entity. We can see this has our scene tag, which I think is probably the convert. You click on this little window icon here. This will show you the actual scene system that this is using. This is the scene selection streaming system. There's 5 entities working on it. Here is our jumping sphere system. Here, here, and here. And I think we can it should show up in our system. Okay, I don't think it actually does. So we can look where that actually is. There. In the default world, whatever. So we can turn this system off. So it's no longer moving, jumping, whatever. We can cut it back on. Okay, so that's the very basics of it. We can look at, I think there's a stress test scene here. We'll see. Hopefully this doesn't like break everything. but there is a stress test for game objects. We'll say whatever. Okay, so this is just going to spawn whatever 10,000 game objects, and then it will kind of animate them, and that's it. We can. I am not very good with the profiler. We'll drop it here for now. And we'll just have stats open here. That'll be fine. Okay, so here we go. So this is running at about 1.5 frames per second. This is updating all of our colors, and eventually we'll try to update these are all individual cubes moving and whatnot. Okay. And again, this is on my several-year-old i7 laptop, NVIDIA 1060 discrete CPU. So let's try this with our hybrid renderer and matching. And here we go. We are doing this at, what, 50-ish frames per second? These are our individual cubes. Yeah. Here we can see a little bit more about what's going on. So job systems, I've got 7 or 8 cores or whatever going on. Not too bad. All right, so let's check out the physics system. Close this. Okay. Up the hub. We'll check out a little bit of the physics system, and then I'll show off there is a dots character controller that Unity actually bought these guys out like a week or so ago. So it is now up on the asset store for free. It is this rival character controller. Dots character controller. Link. It's not free. We'll take a look at some of the samples and whatnot here. This package was like $80 like a month ago, so it's good stuff here, and it will continue to be updated. The developer is now working at Unity full time on this particular asset. Oops, this decides to load up. Okay. All right, so first, what we'll look at here is physics settings. Okay, so our physics step here is basically what will be happening for the actual type we're using. We've got our Unity physics and our Havok physics that we can choose between. It'll also have our gravity, minus 9.8, whether it's multi-threaded, and our actual solver iteration count, which is, I think is more for like ragdoll stuff as well. And these are just various debug stuff that we can actually draw and look at. But for now, we will look here, and then our various shapes here. So we have our physics shape, which is the actual collider. We can change it at any time. We can have box, capsule, sphere, mesh, convex, hole, whatnot. We can give it What is if it's actually a trigger? What are my custom tags? Let's see. We have our materials, which is basically the same as your physics materials. Our collision response is whether you just collide physically or raise events, or you can collide and have collision events, just raise trigger events and none. So if you just need this to be a trigger, you would just have trigger events, and that's it. We also have our friction, and restitution is the bounciness. So anything above 1.0 will actually bounce higher than when it collides with, so it adds energy to it. Below 1.0, again, it will lose its bounciness as it bounces. At 0, it just does nothing. And we have collision filters and whatnot. Motion type for physics body, dynamic, kinematic, static. Smoothing, interpolation, extrapolation, mass, dampening, all that good stuff. Gravity factor. World index, this is if you are having multiple physics worlds. I think there is a demo here that will where you can do like projections into the future for like trajectory indicators for like ballistic stuff. So yeah, so we'll just take a look here. This will be nothing special, just drops. We can change. I don't think we can change on the fly like that. We can change to Havok Physics. I don't think you'll actually see much change here. But we can pick up and throw our things around. I don't, yeah, you do have joints, so that works. We'll look at the use cases, character controller. I guess it is in joints. Where's the ragdoll? There we go. All right. So this is probably, oops, one of the most more impressive demos here. So what we'll do here is we are just going to spawn 50 ragdolls on this stairs, and that's it. So we'll just take a look here at our stats. So here we go. This is on Unity Physics. 75, 80-ish. Once things stop jiggling around, we'll probably hit around 80, whatever. Cool. We can do the same on Havok Physics. Havok Physics is a bit more stable at around 80. FPS. But we can turn this up. Let's double it. So still not bad. We're still at 75-ish. When things stop moving around, we go back up. We can keep going. I think 500. I think it's the max that I actually did on this laptop. And we're still getting 30-ish frames per second. It's not completely blowing up yet. Things are still moving around. They're falling off the edge. I don't know if that's affecting anything or not. But if you ever tried to use game object ragdolls, this is not possible. So this is one of the things that you can pretty much only do with ECS. I think we are still using the Havok Physics. We can look at the Unity one, 500. Okay, half of them fell off the world, but that's fine. Okay. We do have planet gravity, which is not bad. This is basically just kind of a asteroid belt kind of simulator here, which it attracts these things, spins them out. We can look in the dots hierarchy. Again, everything is just kind of happening in the default world. We can look at our systems. We can actually just turn off like all the update. Maybe we can't. We can have a simulation group. The entity command buffer is still buffering. So when we unstop, it replays all that until it catches up. So that's kind of cool. And here we can see here we have a 10,000 little asteroid doodads. And we're 65, 70 frames per second. All right. I don't think there was. We could look at planetary gravity authoring system. So you can just throw your systems and your components into the same file if you want to. This is definitely a viable way of keeping everything together, like all of your planetary gravity stuff is all here in this file. So we have planetary gravity, the authoring component, the system is all right here. So here in the gravity system, we have a couple of attributes here. And this is how you can get more control over your systems on where they run. So this is going to be updating in the fixed time step simulation group, but also updates before the build physics world. So this is going to be setting all of our gravity things before it actually does all of the physics calculations. This entities with name here, this is your job, so you can actually give it a name that you can actually look at in your in the editor here, so you know what it actually is, and it's not just random entity nonsense. And then here is our spawn asteroids. And it's not doing anything too mind-blowing here. This one is using the mathematics.random, which is different from the regular Unity engine.random. Right. All right, and for the last little bit here, we will check out the Bible sample. And this same I want to show you just it comes with the rival character controller asset. Once it finishes importing, so another thing to actually say about the ECS system is that right now it's actually more optimized to run like highly parallelizable operations. So if you have anything that has just one entity, like a character controller, you normally just have just like one player or just a few players. Sometimes you'll end up with actually worse performance than if you had like 10,000 entities, just because your, you know, they call it chunk utilization. If you're not using up all 16 kilobytes of your cache, then that's just wasted space that you're not doing anything with. Okay, finally. So let's look at what we have. Samples. Okay. So I believe this is we do have a couple of AI characters and a I don't know where the actual player is going to end up being. Okay, so for this, what we have is a main game object tag here that is going to want to say yeah. So this will just kind of apply our camera transform into our game object camera system here. So the camera itself does not have to be an actual entity, but our character controller is. There should be a object controller here as well. This is using physics. We've got a couple of NPCs here. And we have platforms and whatnot. If you've ever tried to write your own character controller, you know that moving platforms are kind of crazy to try to get movement right on. There is a vehicle here that also has some vehicle physics. I think you just have to jump onto. Oh my God. And these buttons controls crud. Okay, I don't know how to control the vehicle. But I am super glad that Unity picked these guys up because the character controller is important to most games and also like not exactly intuitive how you would set one of these up in the ECS system. So before we go here, can I climb? Oh, come on. Shoot boxes. Okay. So last thing I want to do here is there is a stress test. Go. So this is yeah. Okay. So we're gonna spawn. I guess we'll just spawn 5,000 dudes here, just on the floor. We're at what, 50-ish frames per second. So yeah, these are all just individual NPC dudes just kind of rolling around in a circle. We can, in our game scene here, we can respawn them. So yeah, they're all doing physics and whatnot. They're not nav mesh pathing, but they are running. We can double this. I have not played many RTSs recently, but 10,000 units on a screen is not half bad, actually. And we're still 30-ish frames per second. Which I am mighty fine with. So yeah, it's 8 o'clock here, so we will just go ahead and wrap it up. We'll probably revisit this in another 6 months or so and see where we are. Hopefully we'll end up with 1.0 by then. But yeah, if anybody has any questions or whatnot, just, this will be up on YouTube. So we also have our Discord channel. You can feel free to hop in and give us a shout. Next month, we are getting our Tilt 5 Kickstarter is supposed to be shipping. So hopefully by this time next month, we will be showing off some AR shenanigans with board games and stuff. So I don't know how we'll end up streaming that. I might just have a webcam pointed at a table or something. But we've got the 4-pack, so we should be cool for doing some Tilt 5 AR stuff. I know the Settlers of Catan is launching with it, or has launched, so board games would be a good application for that. Anyways, thanks you guys for watching, and we will check you out next time.